So section 10.5, we're going to talk about all these angles that are related to a circle. And what you're going to get are a bunch of formulas that you guys are going to have to remember. So this is time to put that memorization technique to work. Okay, so we're going to start off with circles that have angles that are either on the circle or inside the circle. And all four of these formulas that you're going to have here for all four of these situations are going to be very similar to each other. Okay. We already know the first one, the central angle, because we talked about that in chapter 9. And we know that the central angle, which is the angle that the vertex is the center of the circle, it has the exact same measure as the arc that it cuts off. So that formula would be that angle C is equal to the measure of arc AB. Okay, so there's your central angle. And I think you guys remember the inscribed angle. That is the angle whose vertex is actually on the circle, so right here. And if you recall, this angle is going to be half of the arc that is created. So angle C is 1/2 the measure of arc AB. So these should be the familiar ones. Okay, so now we're getting into new territory. So the first one we're going to talk about here that's new is the tangent chord angle. So if you look at this, here's our chord, and then CB is going to be our tangent. And you get this angle, angle ACB right here, that's created. Now, what's interesting to note is that point C, the vertex of this angle, is actually on the circle, which is the same as your inscribed angle, whose vertex is on the circle. So because they have their vertices at the same place on the circle, as opposed to inside the circle, it's going to follow the same formula. So this one was half the arc. If you take half of the arc, you get the angle. Well, same thing here. If you take half of this arc that's created, AC, you'll get angle ACB. So there's the formula. Angle C is equal to half of this arc. Okay, so if you can remember that the position of the vertex, where it is it on the circle, inside the circle, at the center of the circle, outside of the circle? The formulas are all going to be very similar to each other in that respect. Okay, so inscribed angle and tangent chord angle have the same formula. Now we're going to go over here to the chord angle. And this is an angle that's created by two chords drawn in a circle. And we want to make sure that the two chords are not the diameters, because if they're the diameters, then they go through the center of the circle, and all the angles that are created are central angles. So this would not be fun. It would be very boring. So in this case, we have this point right here, E, where the two chords intersect. And what we get are two pairs of vertical angles. And we know vertical angles are congruent. Okay, but what we also get are some arcs. So we have arc AB and we have arc DC, which both of those arcs are going to relate to these vertical angles. And then we have arc AD and arc BC, and those two arcs relate to those two vertical angles that are opposite them. Okay, so now the formula that we're going to come up with is for just solving one angle. So I'm going to use angle AEB as our example, but it could have been the same formula if we were looking for angle DEC or angle AED or angle BEC. Okay, just follow the pattern. All right, so if we look at what this pattern is, it says that if you're looking for this angle, and I'll just kind of highlight it, this angle right here, AEB, then what you're going to do is you're going to take the two arcs that are associated with it, so arc AB and arc DC, which is opposite the vertical angle to that one, okay? And you're going to add them together and divide by 2. Basically, you're taking the average of the arcs. Okay, so whatever this measure is, plus that measure, divided by 2, is going to be this angle right here, which is also that angle, because they're vertical angles, right? Now, had we wanted to figure out this angle right here, and you were given arc AD and arc BC, so what if we had done this? They were looking for this angle right there, then you would have to know this arc, and you would have to know that arc, because those are the two arcs opposite those vertical angles. Okay, so you would say half of the sum of AD and BC would equal that angle. Okay, so let's do an example. Why not? What if I gave you that this arc is 40 and this arc is 100? Figure out the measure of angle AEB. Okay, so using our formula, angle AEB is going to be 1/2 the 40 plus the 100. So that's 140 divided by 2, which is 70. So you can see it's really not that hard. You just have to plug in the numbers and do the math. Okay, let's now switch gears to angles that have vertices outside of the circle. This we have 3 different situations. But what you're going to notice is since all these angles are outside of the circle, they're all going to have the same exact formula, which is really nice because that makes remembering it a lot easier, right? So let's look first at our secant angles. So we have 2 secant segments right here, AB and CB. And because they pass through our circle, we get 2 arcs. Well, actually we get 4 arcs, right? But the 2 arcs that we're going to be concerned about are the arcs that are created that are opposite our angle. So these are the 2 arcs that we're going to be concerned with. I don't care about these 2 arcs on the sides. So what we're going to do to figure out the measure of angle B is we're going to say that angle B is equal to 1/2 the difference of these arcs. So you're always going to take the larger arc and subtract the smaller arc. So in this case, that was arc AC minus arc DE. Okay? So let's see, if we had an example here where I told you arc AC is 120 degrees and arc DE is 50 degrees, if we wanted to figure out the measure of angle B, we plug it in, 1/2 of 120 minus 50, well that's 70 divided by 2 is 35. So angle B would measure 35 degrees. Okay? Now, the tangent secant angle is going to follow the same idea. It's just that the arcs that are created are a little different. So here's our secant right here, which cuts through the circle. But then our tangent, remember, only intersects the circle at one point, so it's not going to cut through and create this other arc on the other side. But what you got to think about, this point right there, that point of tangency, you're going to break that up into 2 arcs. So there's the arc from A to C, and then there's also this arc from D to C. And those are the 2 arcs that we're going to be talking about. And hopefully you can see that this arc AC is bigger than this arc DC. So the formula, once again, is 1/2 the larger arc minus the smaller arc. So same formula, right? Same exact formula. It's just that this arc right here and that arc are created differently than these 2 arcs that you have. Okay, so now when we go down here to the tangent angle, once again, it's going to follow the exact same formula, 1/2 larger arc minus smaller arc. Only this time, you have to look at this point of tangency and that point of tangency to get your 2 arcs. So here's one arc, the really big major arc, going all the way around, okay? And then we also have this little minor arc, which is right here, okay? So it ends up looking like we're using the entire circle, and we are. So the formula, 1/2 the major arc, ADC, and then you subtract the minor arc of AD. C. So all of these formulas very similar to each other. 1/2 larger arc minus smaller arc. You just have to figure out how do you get those two arcs based off of what segments do you have. Okay, so your job is to remember all of these. There were 7 formulas, 4 on the first slide, 3 on this one. Remember which formula goes with which angle, and then know how to plug in the numbers and solve accordingly. Not too bad, right? And just think, no proofs, so you're good. All right, that's it for now. Bye.